In this video, I'm going to start the discussion of chapter 14 in the book by Shankar. And this is a chapter on the topic of spin. So spin is a very unique quantity in nature that has the same properties of angular momentum, but it's not really an angular momentum. Unfortunately, when it was developed, they realized that the mathematics of spin were very similar to angular momentum, and so it was called spin. And there was some idea that it was actually a like rotational angular momentum as opposed to a revolution, but that doesn't actually work out physically. So the classical analogy of spin is that if you look at something like the solar system, then what you have is you have the sun around the revolving around the sun is the Earth, and so the Earth orbits the sun with an angular momentum, and this would be analogous to our orbital angular momentum that we worked on in chapter 12. Which was basically L squared LZ. So in this case, the orbit of the Earth creates an angular momentum LZ. And that seems analogous to what it goes on in the atom, even though the atom is not a solar system. The electrons are still creating this system where the electron is orbiting at a large distance from the nucleus of the atom. So then the idea of spin is that if we give a rotation to the Earth, so if the Earth is now rotating around on its own axis, then the idea is that you would then have some sort of rotational angular momentum as opposed to orbital angular momentum, which we could label as, like, say, SZ. And this is kind of what we would expect, that maybe the electron has its own rotation to it, giving it an extra bit of angular momentum as in addition to its orbital angular momentum. However, this analogy fails because the electron is a point particle, meaning that it has no radius. So it's kind of difficult to rotate if it doesn't have any spatial dimension to it. There's no, it's a point, there's no rotation. It's only when you extend out some distance r away that you can get some sort of rotation around it. So since the electron has no size to it that we know of, or at least at the level of 10 to the minus 18 that we've been able to measure, then the idea is we still consider it to be a point particle. So instead, spin has another property. So it's actually maybe easier to think of spin not as an angular momentum, but as a generator of magnetic fields. And so now, if we think of the electron now as a bar magnet, like this, with a north and a south pole, then it has some directionality to it, which we could call now SZ. And so now if I put a magnetic field across this magnet, so I'll make my magnetic field red. So if there's some sort of external magnetic field going in this direction, then the consequence is going to be that I'm going to rotate the magnet, I'm going to align the magnet in the direction of my magnetic field. Now I've lined up my magnet. And so that's how that's our connection with spin, is more of a magnetic property. And we do know that that magnetic objects carry a magnetic moment when put inside of an external magnetic field will rotate and align themselves with it. It also is actually pretty clear connection now with this magnetic analogy that there can be two orientations. I can orient the electron's bar magnet either, pointing up or pointing down. And then once I put it in an external magnetic field, it's going to either switch from pointing up or pointing down. It's only going to be pointing in the direction, basically parallel or anti-parallel to the direction of this magnetic field. And actually, that's one of the earliest cases that there is experimental evidence that we needed spin was something called the Stern-Gerlach experiment. So what Stern and Gerlach, those two people, Dr. Stern and Dr. Gerlach, what they did was to basically have a beam of particles traveling, a beam of atoms, and then what they did was they took this beam of atoms and they put it inside an asymmetric magnetic field. So I'm basically creating this magnet here, where if I now draw the magnetic field lines, let's say this is north and this is south. So now I've got these magnetic field lines, which are going from the North Pole to the South Pole. And so basically what that does is that these atoms, even though the atoms have no angular momentum, no orbital angular momentum, so they set the angular momentum to zero, they basically picked a spherically symmetric atom, which they were allowed to go through this magnetic field. And the result was, when they put a fluorescing screen over here, that the beam actually formed two spots. So some of the particles, the atoms, went up, and some of them got bent down. So again, if you think of your atoms as a little magnet, a north and south pole magnet, then some of those atoms would be pushed upward, and the other ones would be pushed downward, depending on their orientation when the beam entered in this magnetic field. Actually, it should be a 50-50 split. So half of them would go up, and the other half would go down. Because you think if I have an ensemble of atoms, then half of them are going to be, their magnets are oriented north up, and half of them are going to have their magnets oriented north down. So obviously there's something in nature, which now we're going to call spin, which orients these atoms in one direction or another, and that orientation is basically has a magnetic property to it. So in the end, what we get is we get a degeneracy of all energy level states. Now, some of them are going to be pointing up, some of them are going to be pointing down. And so what happens is if I look at my energy levels, so I have N, L, and M. So I have my principal quantum number. So let's say that N equals 1. And then the only possibility is L equals 0. The only possibility is M equals 0. But now that M equals 0 state has two possibilities. Once I put a magnetic field on it, I now have a 1/2 h bar amount of angular momentum. And so then if I look at the next energy level, so this one would be N equal 2. The possibilities for L are 0 or 1 because of the degeneracy of angular momentum. The only possibility for M would be 0 if L is 0. However, if L is equal to 1, I could have an M equal 0 and an M equal to 1. No, I'm sorry. So the only possibilities are M's minus 1 or 1. And so then we get the degeneracy for spin. We have a plus and a minus. And this one splits off to plus h bar over 2 minus h bar over 2 plus h bar over 2 minus h bar over 2. So now you can see all the degeneracies. There's the principal quantum number degeneracy associated with the total energy. There's the degeneracy of the angular momentum and its projection in the z direction. And then lastly, there's this degeneracy with the spin orientation. So that's kind of the need for studying the spin. It's been observed that there is this property when they're studying spectroscopy of atoms that we could look at an atom with a certain total energy, which is the principal quantum number n, and then associated with that there are certain levels of angular momentum, L. We know then that I can actually write it down. So we know that L can't be bigger than n minus 1. We know that M has to be in between minus L and L. And now we see that spin, which I haven't quite given it a label yet, but the spin, at least for the electrons, is plus or minus h bar over 2. So this is true for electrons, for protons, for neutrons, basically any of the fermions. We can have spin of other combinations, but that's only when you get composite particles. So if I now put a proton and a neutron together and form the nucleus of deuterium, now this object can have a spin of basically adding up the spin of the proton and the neutron. Then we can have spins of positive 1, negative 1, or 0. So if I draw the spins of the proton and the neutron, so in this case, the proton could be spin up, the neutron will be spin up, the proton will be spin down, the neutron will be spin down. And in this case, for 0, I have two possibilities: proton spin up, neutron spin down, or proton spin down, neutron spin up. So the fundamental unit of spin is h bar over 2, and that's for all your fundamental particles, fundamental fermion particles, these antisymmetric particles of the electron and the quarks. And then once you start getting the composite particles, like the proton and the neutron and the deuterium, tritium nucleus, carbon nucleus, now you have to start adding up the spin. And since it has the same mathematics of angular momentum, then it's going to have basically, you can calculate the same way you would the orbital angular momentum. So in the next video, I'm going to go on to the mathematics of spin and how we're going to derive the wave functions for the spin.